Tonight, we're going to leave home. Not just the solar system, not just the familiar map of nearby galaxies, but the calm, ordered heart of the Milky Way itself. You're going to step from our relatively quiet galactic centre into a place so distant that its light began travelling toward us before the Earth even existed, and discover a galactic heart that breaks every rule our own seems to follow. Before we get started, picture what most people expect to see at the edge of the observable universe. Faint smudges, tiny blurry islands of stars barely separated from the cosmic background. Young galaxies that should be small, messy and underdeveloped, with central black holes just starting to grow. That's the prediction. That's the model scientists have trusted for decades. Now, the reality. JWST focuses its infrared eyes on one of those smudges, a system less than 1 billion years after the Big Bang. Light has been on the road for over 12, even 13 billion years, crossing almost the entire history of space to reach a single mirror. And when that light is spread into spectra and sharpened into images, the galaxy's centre does not look like a timid beginning. It looks overgrown, hyper-compact, violent. Instead of a calm, bar-dominated core like the Milky Way, JWST reveals a tiny nucleus packed with stars, choked with turbulent gas, and dominated by a central black hole that seems far too massive for such a young galaxy. No one predicts a monster like this so early. No one expects a galactic centre that already rivals or even exceeds the mass of the black hole in our own system's core. This is where the contradiction hits. Standard models say galactic centres grow slowly and gradually through countless mergers and steady feeding over billions of years. The Milky Way fits that narrative. A relatively gentle bulge, a black hole that sips more than it erupts, a region that, on cosmic scales, feels almost civilised. But when JWST turns the universe into a time machine and looks back to these first billion years, the script falls apart. Instead of orderly growth, there is chaos. Starburst rings that burn through gas faster than models allow. Chaotic inflows and outflows, driven by the black hole's radiation and wind, reshaping the core. A nucleus so dense that the usual boundaries between galaxy and central engine blur. By the end of tonight, you're going to understand how this spacecraft can see that far back, what exactly was discovered in this alien galactic heart, and why it might mean that our Milky Way is not the template for galaxies, but the odd one out. Now let's begin. To understand how strange that distant galactic heart is, you first need a clear picture of home. Our own galactic centre, buried in the constellation Sagittarius, looks calm enough that for decades scientists treated it as the standard template. A supermassive black hole, a bar of stars, a rounded bulge, a nucleus that seems frozen on human timescales. At the very centre sits Sagittarius A, a black hole with about 4 million times the mass of the Sun packed into a region smaller than our solar system. Stars whip around it on orbits that take just a few years. Gas spirals inward. Space itself is curved into a gravitational well so deep that not even light can escape once it crosses the boundary. By everyday standards, this is extreme. But in the catalogue of galactic centres, this used to look almost boring. Across different wavelengths, that boring core turns into a layered radiant engine. In radio, huge interferometers map the region around Sagittarius A, tracing jets, arcs, and filaments of charged particles threaded by magnetic fields. In 2022, the Event Horizon Telescope produced a radio image of the black hole's immediate environment, a glowing ring of emission surrounding a dark shadow. It is the closest thing to watching gravity itself sculpt light. Move to infrared, and the picture changes again. Dust that blocks visible light becomes transparent, revealing crowded starfields near the nucleus. The bar of stars that cuts across the Milky Way's centre emerges, funneling gas inward like a conveyor belt. The bulge looks smooth from a distance, but in infrared it breaks into clumps and streams, a fossil record of past mergers and slow, steady evolution. Push to X-rays, and the core lights up with a faint, flickering halo. Spacecraft like Chandra and XMM Newton have discovered hot gas at tens of millions of degrees, modest flares from Sagittarius A send echoes of past outbursts. There are traces of violence here, but nothing like a quasar. The black hole is underfed. The wind from the center is present, but not overwhelming. For a galaxy this massive, the nucleus is on low power. That combination led to a powerful assumption. If the Milky Way looks like this, then many mature spiral galaxies must follow the same pattern. In the standard model, galaxies assemble gradually. Small proto-galaxies merge. Gas cools and settles into a rotating disk. Over billions of years, a bar forms, a bulge grows, and the central black hole slowly gains mass from infalling gas and disrupted stars. Designed for slow evolution, expected to age gracefully. Absolutely no one anticipates a galactic center that behaves like a cosmic detonation instead of a quiet anchor. Yet that is exactly what JWST is now revealing at the edge of the observable universe. The next step is to compare this normal blueprint with a nucleus so compact, so overgrown, and so violently bright that it forces the entire mission of galaxy formation theory to confront a new boundary between order and chaos. At the edge of the observable universe, JWST has just pointed at what looks like a faint smudge, and uncovered a galactic heart that breaks every rule our own center seems to follow. This is not a gentle bar of stars circling a quiet black hole. This is a compact, blazing core, less than 1 billion years after the Big Bang, already acting like a fully grown monster. Now, let's begin. In JWST's deep infrared view, this young galaxy's nucleus collapses into a tiny, brilliant knot. The light is so concentrated that scientists can tell there is a central engine dominating everything around it. Spectra from NIR spec show broad emission lines, smeared out by gas whipping around at thousands of kilometers per second. That broadening is the calling card of a massive black hole, already comparable to, or even larger than, Sagittarius A in the Milky Way. That alone is unsettling. Designed for a universe where black holes grow slowly as galaxies merge, standard models predict that at this early time both the galaxy and its central object should be small, clumpy, still assembling. Instead, JWST has discovered a core that looks overmassive for its host, like a heart that grew faster than the body around it. And it is not just the mass. The region right around this black hole is a cauldron. The infrared light reveals extreme star formation packed into the inner few hundred light years, a starburst ring so dense that new suns are igniting at rates dozens or even hundreds of times higher than near our solar system's calm orbit. Gas clouds are being compressed, shredded, and accelerated. Some streams plunge inward toward the event horizon, others blast outward as winds, racing away at astonishing speeds that rival the fastest outflows seen in much later galaxies. No one expects this level of organization and violence so early. No one predicts a nucleus this compact, this bright, this mature, when the cosmic clock has barely started. And absolutely no one anticipates a black hole that seems to have leapt ahead of its own galaxy in the race to grow. This is where the real mystery crystallizes. How did this black hole gain so much mass so fast when there has been so little time since the Big Bang? Why is the core so compact and dense, instead of puffy and irregular the way simulations of young galaxies usually show? What does this say about the entire story of galactic evolution that textbooks outline from neat, hierarchical mergers? Tonight, we're going to follow that puzzle all the way down. By the end of tonight, you're going to understand 7 major ideas JWST has forced scientists to revisit. How black holes seed and grow, how star formation behaves under extreme gravity, and whether the dark matter scaffolding in galactic centers is far stranger than the smooth halos everyone assumed. The next step is to walk through those 7 shocks, one by one, and see why this single baby galaxy might be the first warning that our model of the universe's growth has a hidden fault line. Those 7 shocks all point to one uncomfortable possibility. The Milky Way may not be the gold standard galaxy everyone treats it as. For decades, scientists have quietly assumed that our spiral, with its neat arms and calm central bar, is a pretty average citizen of the cosmic city. When a distant smudge is discovered, the first instinct is to scale it to the Milky Way and call that a reasonable starting point. Expectation. The local neighbourhood is typical. Reality. This one galaxy at the edge of the observable universe is threatening to blow that assumption apart. In our own solar system city, the galactic centre looks almost restrained. A bar of stars, a modest supermassive black hole. Gas flows that, while complex, are not tearing the system apart. JWST, staring billions of light years beyond, has now found a galactic heart that is the opposite. Compact, hyperdense, a black hole already rivaling or exceeding the Milky Ways, packed into a galaxy less than 1 billion years old. No one predicts that. If the standard picture is right, black holes should grow slowly as galaxies merge, as gas trickles inward, as star formation and feedback carefully regulate the pace. But the spectra from this object tell a different story. Furious starbursts right in the core, turbulent gas whipped into chaotic flows, violent winds punching out of the nucleus. This is not a quiet bar. It is a maelstrom. Tonight, we're going to treat that difference as more than a curiosity. Because if early galactic centers routinely look like this, then the whole timeline of cosmic evolution compresses. Supermassive black holes do not have 10 billion years to bulk up. They have a few 100 million. Star formation does not meander along in gentle waves. It detonates in brief, extreme episodes that reshape the entire system. By the end of tonight, you're going to understand why that compression is so dangerous for our current models. Theories tuned to the Milky Way's leisurely pace suddenly have to explain how a young galaxy grows a monster that outmasses its own stellar body, how dark matter halos funnel gas inward fast enough, how feedback from that central engine doesn't just blow the whole galaxy apart. And there is a deeper, more personal consequence. If our galaxy is odd, if our calm bar and relatively quiet core are the exception rather than the rule, then our local patch of space may be lying to us. The solar system sits in a serene disk, orbiting a centre that no longer reflects how most galactic hearts behaved when the universe was young. The story told by the Milky Way might be a late-time epilogue, not the main plot. No one expects a single faint smudge in a JWST deep field to threaten the narrative for every galaxy, every black hole, every star-forming cloud. Yet that is exactly what is happening. To understand this alien galactic heart, to know whether it is rare or common, one question comes first. What kind of telescope can pull a compact raging core out of nearly 13 billion years of darkness? Before we get started on the galaxy, we have to understand the machine that discovered it, and why it was built to see what Hubble could never reach. The answer begins with a telescope that changed everything and then hit a wall. Hubble turned the sky into a time machine. It mapped the structure of the solar system's neighbourhood, weighed planets around distant stars, and pushed deep fields so far that thousands of unseen galaxies suddenly appeared. But Hubble has a handicap. It lives mostly in optical and near-ultraviolet light. That is perfect for crisp, colourful images, but terrible for two things that matter most for early galactic centres: dust and distance. Dust in space is not gentle. It blocks and scatters visible light, hiding the crowded cores of galaxies behind thick, dark lanes. Hubble can see hints around the edges, but the most buried regions, the true central engines, remain silhouettes. Go farther out toward the edge of the observable universe, and a second problem appears. The galaxies are there. Their light is not, at least not where Hubble is looking. Here is where cosmology quietly rewrites the rules. As the universe expands, it stretches the very waves of light crossing it. Photons that left a young galactic centre in fierce ultraviolet get pulled, over billions of years, into the infrared. The farther the galaxy, the more that light is redshifted. From Earth's perspective, the first compact cores are broadcasting, but they are broadcasting on the wrong channel for Hubble. No one expects an optical telescope to see a signal that has been dragged entirely out of its band. Tonight, we're going to follow the mission that was designed to catch that missing broadcast. The James Webb Space Telescope is not just a bigger Hubble, it is a different kind of spacecraft tuned from the ground up for infrared. A 6.5-metre segmented mirror, made of gold-coated beryllium, gathers more than 6 times the light Hubble can collect. A sun shield the size of a tennis court unfolds to block the heat of the sun, earth and moon all at once, dropping the observatory into permanent artificial night. Then comes the pattern interrupt. Webb is not in Earth orbit at all. It sits near the second Lagrange point, L2, about 1.5 million kilometres beyond our planet, where the gravitational pulls and orbital motion line up just right. There, the telescope can face deep space continuously, while its instruments are cooled to cryogenic temperatures. Any warmer, and the mirror would glow in infrared, drowning out the faint signal from those distant galactic hearts. By the end of tonight, you're going to understand why its instruments read like a blueprint for dissecting galactic centres. NIRCam takes ultra-deep infrared images, resolving the compact bulges and surrounding star-forming rings in galaxies less than 1 billion years old. NIRSpec spreads that light into spectra, letting scientists measure the motions, chemical fingerprints and hidden black hole signatures in their central regions. MIRI, reaching to even longer wavelengths, peers through the heaviest dust, revealing buried, obscured cores that optical views miss entirely. Now, let's begin to use that power. Webb was not built just to take prettier pictures. It was built to cross a boundary Hubble could never pass, to uncover the hidden structure of the first galaxies, and to expose the overactive central engines that were already raging when the universe was still young. Crossing that boundary means doing something that, at first glance, looks almost pointless. You take one of the most powerful telescopes ever built and you aim it at nothing. A patch of sky with no famous nebula, no bright planets, no obvious galaxy cluster, just black. Or so it seems. This is the logic of a deep field. Instead of slewing from target to target, Webb locks onto an apparently empty region and stares for tens of hours. Photon by photon, the faintest signals in space pile up on its detectors. What begins as darkness slowly fills with ancient light. With galaxies so distant their glow has been stretched into the infrared by the expansion of the universe. These fields are not chosen at random. Before we get started, picture the sky as a crowded photograph. Nearby stars blazing in the foreground, dust veils from our own solar system, and Milky Way streaking across the frame. Scientists carefully pick windows where that clutter is minimized. Low foreground dust. Few bright foreground stars. No glaring nearby galaxies to drown the view. The result is a clean line of sight, a narrow keyhole through which Webb can probe far beyond our own system, straight into the early cosmos. In those directions, the background is rich with distant structures, galaxy groups, protoclusters, filaments of matter where gravity has already begun to sculpt the large-scale web. These are ideal places to catch galactic centers in the act of forming, because the environment is dense, chaotic, and evolving fast. Tonight, we're going to lean on one more idea that deep fields make visceral: look-back time. When Webb records a galaxy at redshift 10, that galaxy is not just far away in space, it is far away in time. The light has been travelling for more than 13 billion years. By the end of tonight, you're going to understand that when those photons left, the universe was only a few 100 million years old, less than 1/10 of its current age. Expectation versus reality becomes brutal here. Models say that at such early times, galactic centres should still be messy, low-mass seeds, small black holes, modest star formation, nothing like the massive ordered bulge at the heart of the Milky Way. But as Webb's deep fields accumulated, something began to stand out. Among the countless smudges, astronomers noticed peculiar compact sources, tiny pinpoints with central regions far brighter than their outer disks. No one predicts that level of concentration so early. No one expects that much energy coming from such a small volume. These were flagged for follow-up with spectroscopy. With NER spec, scientists could dissect the light, measure redshifts, and read the fingerprints of hot gas swirling near hidden engines. Some showed extreme line widths, signatures of fast-moving material under intense gravity. Others revealed furious starbursts packed into regions only a few hundred light-years across, and in one deep field, a single faint blotch that Hubble barely registered as a whisper turned, under JWST's gaze, into something else entirely. A compact galaxy with a central heart so overpowered, so prematurely evolved, that absolutely no one anticipates what it implies. That is the galactic centre waiting in the data, and the closer you look, the less it behaves like anything in our own calm core. To make sense of that alien heart, you have to face a problem at the core of modern astronomy. How do you weigh something that, by definition, does not let light escape? Black holes do not glow. They carve a boundary in space where even light cannot return. So scientists never see the black hole itself. They see what its gravity does to everything around it. Now, let's begin. Imagine a city at night where every building is invisible, but every car's headlights are blazing. You can't see the buildings, but you can watch how the cars move, how they whip around corners, how fast they orbit the dark downtown. In space, the cars are gas clouds and stars. Their orbits, their speeds, their violent accelerations become the only honest reporters of the mass hiding in the dark. This is where spectra come in. Split the light from a galaxy into its colours, and you get a barcode of spectral lines. Each line comes from a specific atom or ion. When that gas moves, those lines shift. If it's racing toward you, they slide to shorter, bluer wavelengths. If it's fleeing, they stretch redward. Measure that Doppler shift with precision, and suddenly you know the velocity of gas that would otherwise be just a blur. But it's not only where the lines land, it's how wide they are. A narrow line means most of the gas shares a similar speed. A broad, smeared-out line means chaos. Gas on the near side rushing toward you, gas on the far side racing away, all trapped in a deep gravitational well. The broader the line, the faster the motion. The faster the motion, the more mass must be lurking in the centre to keep that gas bound. Tonight, we're going to treat those lines as a dynamical seismograph. Emission from ionised oxygen, hydrogen, neon streaming near a galactic core can be modelled like a rotating disk, a turbulent wind, or a compact starburst. Change the assumed black hole mass, and the predicted line widths and shapes change. Adjust the density of the surrounding core, and the brightness profile shifts. By matching models to the actual spectrum, scientists can infer both the weight of the central black hole and how densely packed the inner few hundred light-years really are. Here is where JWST changes the game. Its near-spec instrument can take spectra not of an entire galaxy smeared into one signal, but of tiny patches, effectively isolating the central few hundred or thousand light-years, even in galaxies billions of light-years away. Instead of averaging the calm outskirts with the raging centre, it can zoom in on the true nucleus, where gravity is in charge. By the end of tonight, you're going to understand why that matters. Because when astronomers pointed NER spec at this distant compact galaxy and ran the models, the velocities were extreme, the line widths were enormous, and the implied black hole mass and core density were absurdly large for such an early universe. No one expects numbers like that less than 1 billion years after the Big Bang. No one predicts a galactic centre that heavy, that fast, that soon. And absolutely no one anticipates what it means for how galaxies like our own solar system's home grew up. To see why this is so disturbing, you have to rewind to the standard story. Before we get started on the anomaly, you need the script that every textbook, every simulation, every galaxy formation mission has been running for decades. In that script, the universe starts small. Tiny clumps of dark matter pull in gas, forming the first star clusters and miniature protogalaxies. They are fragile, dim, and everywhere. Over hundreds of millions, then billions of years, these little systems collide, merge, and stack like cosmic building blocks. Small galaxies build medium galaxies. Medium galaxies build giants. The Milky Way is supposed to be the end product of this long hierarchical construction project, not something you can speedrun. At the same time, deep in those young galactic centers, the first black holes are supposed to light up. By the end of tonight, you're going to understand why their origin story matters so much. In the standard picture, the seeds start modestly. Some form when the very first, extremely massive stars in the universe die, collapsing into black holes tens or hundreds of times the mass of the Sun. Others may appear when pristine gas in the early universe falls directly into a compact core, skipping star formation and forming seeds in the range of 100,000 solar masses. Those are the heavyweights. Even then, they are still just seeds. From there, the growth is supposed to be patient. The black hole sits in the middle of its galaxy, feeding on infalling gas, swallowing the occasional star, and merging with other black holes when galaxies collide. Sometimes the feeding rate surges and the nucleus blazes as a quasar. Most of the time, it glows more quietly. Over billions of years, this steady diet, plus rare but dramatic mergers, slowly inflates the black hole from a seed to a supermassive giant. In this framework, galaxies and their central black holes are partners. As the galaxy's bulge grows in mass and density, its central black hole grows too. Observations in the nearby universe show tight correlations. The bigger the galaxy's central bulge, the bigger the black hole, almost as if they are negotiating how much mass each is allowed to keep. Feedback from the black hole's radiation and jets helps regulate star formation, while the galaxy's gas supply sets the black hole's fuel budget. It is a coevolution, a long conversation written in gravity and light. And crucially, the timescales are slow. To reach the mass of Sagittarius A and about 4 million suns, the standard models typically require several billion years of mostly steady growth, punctuated by rare feeding frenzies when galaxies interact. That fits the Milky Way's age. It fits the calm state of our present-day solar system's home. Now, let's begin to see the problem. When a galaxy less than 1 billion years old hosts a black hole rivaling or exceeding Sagittarius A, the entire growth history just described is crushed into a cosmic blink. No one expects seeds to grow that fast. No one predicts that much accretion before the universe has even finished reionizing. And absolutely no one anticipates a galactic center that seems to run the movie of galaxy evolution on fast forward, forcing scientists to ask whether the standard timeline is wrong, or whether something even stranger is happening at the edge of the observable universe. So what happens when that impossible galactic seed is buried under its own creation, when the very material that feeds it also hides it? Tonight, we're going to follow James Webb straight into that choke point, the dust-choked heart of a young galaxy less than 1 billion years after the Big Bang. Early galaxies are messy. Their central regions are crammed with cold gas, collapsing clouds, and newborn stars blasting out radiation and wind. The same process that builds planets in a solar system, dust grains clumping, gas collapsing, plays out on a galactic scale, but amplified. Near the core, gravity funnels everything inward, so the black hole feeds, stars ignite in compact clusters, and the space between them fills with soot-like grains forged in earlier supernova. In visible light, that chaos goes dark. Dust grains are just the right size to scatter and absorb optical photons, So to a traditional telescope, the central few hundred light-years can look dim, diffuse, even quiet. The true concentration of mass and energy is wrapped in a cocoon. From Earth, through Hubble's eyes, this distant galaxy could pass for a modest, slightly blurry smudge. No one expects that smudge to conceal a nucleus, outshining entire nearby galaxies. Infrared changes the rules. The same dust that blocks starlight does not stay cold. It absorbs harsh ultraviolet and optical radiation from young stars and the accretion disk around the black hole, then re-radiates that energy as a warm glow in the infrared. Longer wavelengths slip between dust grains instead of bouncing off them. By the end of tonight, you're going to understand why that shift in wavelength is like turning on the lights in a smoke-filled room. This is where JWST's NIRCam steps in. Its near-infrared images slice through the haze and resolve the galaxy's center into a compact blazing knot. Structures that looked smooth now break into clumps and rings, hinting at starburst rings and spiraling gas flows feeding the core. The boundary between galaxy and nucleus tightens. What seemed spread over thousands of light-years collapses into a region only a few hundred across. But images alone do not tell you what that glow is made of. Now, let's begin to dissect it. NIRSpec, JWST's spectrograph, takes that infrared light and splits it into thousands of wavelengths. Emission lines from hydrogen, oxygen, and neon reveal gas temperatures, densities, and motions. Broad high-velocity features betray an accreting black hole. Narrow, intense lines signal furious star formation. Together, NIRCam and NIRSpec turn a single bright pixel into a map of physical conditions at the very center. Here comes the pattern interrupt. The expectation is a gentle, slowly growing core, a baby version of the Milky Way's relatively calm, bar-dominated center. The observation is a compact, raging furnace, a hyperactive nucleus where overmassive black holes, starburst, and choking dust all coexist in a volume that should not host that much power so early. When JWST peeled back the dust, it did not discover a quiet heart. It uncovered a galactic engine running at full throttle, long before the universe was supposed to allow it. The furnace has a name. Buried in those JWST spectra is a single, brutal number, the mass of the central black hole. From the broad emission lines, from the way gas is whipped into a relativistic whirl, scientists infer a monster weighing in at around 1 billion suns, not a few million. Not comparable to Sagittarius A, 10 times heavier than the black hole at the center of the entire Milky Way, in a universe that is still in its cosmic childhood. Now, let's begin. The host galaxy itself is tiny by local standards. Its total stellar mass, all the stars combined, might only be a few billion solar masses. That means the black hole is not a footnote in the mass budget. It is a rival. In the Milky Way, Sagittarius A is about 4 million solar masses, a fraction of 1% of the bulge. Here, the ratio is pushed toward 1 part in 10, or worse. In some reconstructions, the central object threatens to outweigh the entire visible core. In the nearby universe, that does not happen. The rule of thumb is simple. The bigger the bulge, the bigger the black hole, but always as a small fraction, designed for a quiet equilibrium between stars and central gravity. The reality in this early system is different. The boundary between galaxy and black hole dominance has been crossed. The nucleus looks more like a black hole with a galaxy, not a galaxy with a black hole. Before we get started on wild new theories, there is a hard physical break every accreting black hole must obey, the Eddington limit. Pour gas onto a black hole and it heats up, shines, and that radiation pushes back. There is a maximum rate at which gravity can win over light. Grow too fast, and the outgoing radiation blows away the fuel. Even if this object had been accreting at that limit from the moment the first stars switched on, there simply has not been much time. Run the numbers. From a stellar mass seed of 100 suns, growing at the Eddington rate, you struggle to reach 1 billion solar masses in less than 1 billion years. The universe here is younger than that. Some scientists thought maybe the accretion was just briefly super Eddington, or the seed was unusually heavy, a direct collapse black hole of 100,000 suns. But as more JWST galaxies come in, more overmassive cores appear. No one predicts a whole population of early black holes gorging this fast. The reaction is textbook scientific whiplash. First, suspicion. Are the spectral lines contaminated? Are the models for gas dynamics wrong? Is dust tricking the instruments? Then, recalibration. Independent teams refit the spectra, tweak the assumptions, compare with other deep field targets. Finally, a quieter, more unsettling phase. The pattern is not going away. Absolutely no one anticipates that the standard growth story for black holes might fail this dramatically, this early, across multiple systems. By the end of tonight, you're going to understand the leading ideas for how this could happen. But the immediate question hangs over this galaxy like a shadow. If the black hole is already this big, this fast, what did the galaxy have to sacrifice or violently accelerate to feed it? And if this is what one nucleus looks like at the edge of the observable universe, what are we about to discover in the next, even deeper, field? That shadow gets even darker when the camera zooms in. JWST doesn't just see the black hole, it resolves the entire central region into a pinprick of light, a compact stellar core only a few hundred light-years across that outshines the rest of the galaxy's body. From this distance, the Milky Way's bulge would look swollen and soft, a hazy glow stretching thousands of light-years. This thing is the opposite. It's like trading a sprawling continent for a single city block, then discovering that every building in that block is a skyscraper. By the end of tonight, you're going to understand why that comparison is not poetic exaggeration, but a quantitative shock. When scientists translate JWST's brightness profile into a stellar density, the numbers feel almost unreal. In our own bulge, stars are crowded compared to the solar neighbourhood, but there is still space between them. The average separation is measured in light years. In this early core, pack those same stars not across a continent, not even across a country, but into something closer to downtown Manhattan. Imagine the entire population of a planet squeezed into a single tower, floor by floor by floor. This is the signature of a rapid dissipative collapse. Gas didn't leisurely orbit, forming an ordered bar and slowly feeding the center over billions of years. It crashed inward, radiated away its energy, and piled up in the nucleus, where it fragmented and ignited into stars almost on the spot. Tonight, we're going to follow that collapse from a smooth cloud to a blazing knot of suns, because this environment is nothing like the relatively spread-out bulge the solar system calls home. In the Milky Way, orbits in the bar and bulge are organised. They trace graceful paths, like lanes on a cosmic highway. Here, the orbits are more like a rush-hour intersection with no traffic lights. The core looks less like a mature bulge and more like a nuclear starburst cluster. A tightly wound swarm where new stars, old stars and in falling gas all occupy nearly the same tiny volume. No one expects that to be the default outcome. No one predicts that the textbook picture of a calm, slowly grown bulge might be the exception rather than the rule. Yet this galaxy's nucleus, and others JWST has discovered at similar redshifts, hint that early galactic centers were compact, violent and temporarily overbuilt. And that density is not a static statistic. It drives the violence. In a region this cramped, every supernova, every stellar wind, every outburst from the black hole slams directly into neighbouring gas. The result is a feedback loop of shocks and outflows that will reshape the entire system. Now, let's begin to follow those flows outward and see how this tiny, overpacked heart can punch far beyond its own boundary. Those shocks and outflows don't just escape into space. Some of them run into a strange glowing barricade wrapped tight around the centre. JWST's view turns that barricade from a blur into structure. It isn't a random cloud, it's a ring. With NIRCam imaging and NIRSpec spectral maps, scientists can actually trace where the youngest, hottest stars live in this distant system. They light up the infrared like a neon sign. Emission from hydrogen, oxygen, and neon lines spikes along a narrow band encircling the central source. That spike is the signature of very young, massive stars packed into a compact ring or disk, only a few hundred light years across, hugging the black hole's neighbourhood. In the Milky Way, the central few thousand light years form a mix of old stars, modest gas lanes, and a relatively gentle circumnuclear ring. Star formation happens, but it is measured, almost careful. Here, the contrast is brutal. JWST's spectra point to a star formation rate tens, maybe hundreds of times higher than what our own galactic centre manages. Per unit area, this ring is forming stars at a pace that makes the Milky Way's core look like it is on an extended coffee break. By the end of tonight, you're going to understand why that matters. A ring like this is not just a byproduct of chaos, it is an engine. Gas streaming in along larger scale filaments slams into the ring, piles up, and fragments into dense clumps that collapse into stars. At the same time, the ring's gravity and orbital motion can act like a conveyor belt, channeling part of that gas inward, across the final few light years, straight toward the black hole. But this is where the system turns against itself. Massive stars do not live long. Within a few million years, they unleash ferocious stellar wind, then die as supernovae that detonate inside the ring. Each explosion drives shocks back into the inflowing gas, carving cavities, punching holes, and in some directions blowing material completely out of the central region. No one predicts a tidy, one-way feeding lane. The ring feeds the black hole and fights it at the same time. Tonight we're going to use this ring as a kind of diagnostic. It shows a configuration that looks nothing like the Milky Way's calmer, bar-dominated centre. A hyperactive starburst wrapped tightly around a rapidly growing black hole, locked in a feedback loop of fueling and throttling. Before we get started on the larger scales, there is a deeper question hanging over this discovery. Is this chaotic, self-competing engine the exception, or is this how galactic centres usually grow up in the early universe? In the Milky Way's core, gas mostly knows where it's supposed to go. In this galaxy at the edge of the observable universe, the gas behaves like it has torn up the rulebook. JWST's spectra don't show a simple, graceful rotation curve. They show chaos. Now let's begin. When scientists spread out the light from this galactic centre, using JWST's NIRSpec, the emission lines are not narrow and tidy. They are broadened, split, skewed. Some components are racing toward us at hundreds of kilometers per second. Others are blasting away at over 1,000 kilometers per second. In a single pixel of the detector, there are inflows, outflows, and shock fronts colliding in 3 dimensions that the spacecraft can only see in projection. In the Milky Way, the central gas is dynamic, but it mostly behaves. Clouds stream along the bar. They orbit the black hole in a rotating disk, following orbits that, while complex, still look like a system trying to settle into order. Here, the expectation would be the same. A young bar, a forming disk, gas spiralling inward in a relatively coherent flow. The reality is different. The velocity field looks shredded, with clumps of gas moving in opposite directions along the same line of sight. That kind of turbulence is not just messy, it is productive. Compressed by shocks moving at hundreds of kilometers per second, gas clouds can be driven over the threshold where gravity wins and new stars ignite in rapid bursts. A single shock front ploughing through a dense ring near the centre can light up tens of thousands of solar masses of gas in one brief, furious episode of star formation. But those same chaotic winds and collisions also kick gas back out, heat it, and tear apart the very structures they helped create. So the core can never quite relax. Every time gas tries to settle into a stable orbit around the black hole, Another blast wave, another inflow, another collision destabilizes it. No one expects a neat bar-dominated pattern here. No one predicts a quiet, long-lived ring gently feeding the nucleus. Instead, the center cycles between feeding frenzies and violent purges, with the black hole and the starburst trading control of the flow. Pattern interrupt. Imagine rewinding the Milky Way to its childhood and discovering that this was normal. Early galactic centers might not gently evolve into ordered bars. They might pass through dozens of these wild episodes, each one briefly rewriting the mass distribution, the star formation rate, and the growth of the central black hole. By the end of tonight, you're going to understand why that matters. Because to explain this level of chaos, it is not enough to look at one galaxy. The entire framework of galaxy evolution may be tilted toward early extremes, and to test that, the view has to zoom out from this single unruly core to the cosmic population it represents. Now, let's begin. If the previous section showed how extreme this galactic center already is, this one shows what it's doing to everything around it. In galaxy evolution, feedback is not a review, it is violence. In this context, feedback means energy and momentum injected back into the surrounding gas by the central black hole and by massive short-lived stars. As matter spirals into the black hole, it releases radiation and launches winds and jets. As giant stars live fast and die in supernovae, they blast shockwaves into the interstellar medium. Together, they heat, stir, and sometimes expel the very gas that built them. JWST lets scientists watch that process ignite in a galaxy less than 1 billion years after the Big Bang. Through NeoSpec, the spectra from this compact core do not show calm, narrow lines from gently orbiting gas. They show broadened emission lines, spread over hundreds of kilometers per second in velocity space. In some directions, those lines are skewed and blue-shifted, meaning gas is racing toward us, out of the galaxy, rather than quietly circling inside it. Zoom in on specific traces of ionized gas, and the picture sharpens. Extended structures of hot, glowing material stretch away from the nucleus, like cones or bubbles carved into the early cosmic web. The geometry is not random. It lines up with where the central engine would naturally drive a wind. The result looks less like the Milky Way's calm, bar-dominated center, and more like a miniature quasar outflow, already punching holes through its host. The comparison to the nearby universe is where the shock really lands. In local active galaxies, such powerful outflows are usually linked to supermassive black holes that have had billions of years to grow, and to galaxies that have already gone through multiple rounds of mergers and starbursts. Tonight, we're going to confront a different timeline. Here, less than 1 billion years after the universe switched on, the inferred power of these winds rivals or exceeds those mature systems. No one expects that level of feedback so early. No one predicts that a young galaxy at the edge of the observable universe would already be driving galaxy-scale weather. The implication is brutal. By the end of tonight, you're going to understand that this galactic center may already be self-regulating. The same black hole and starburst that demand huge inflows of cold gas are launching winds strong enough to heat, disrupt, and expel that fuel into intergalactic space. The system is pressing the accelerator and the brake at the same time. If feedback this violent switches on early, it could help explain a long-standing mystery. Why some galaxies end up quiet, disk-dominated and Milky Way-like, while others balloon into massive ellipticals with dead red stellar populations. Does early feedback lock in a galaxy's fate? Or is there an even deeper boundary in the physics that JWST has only begun to expose? If early feedback can lock in a galaxy's fate, this object shows what happens when the accelerator sticks down and never lets up. Because when JWST zooms in on its center, the picture is not of a messy, formless cloud. It looks organized. Alarmingly organized for a universe still in its infancy. The imaging hints at a compact, bright knot right at the core. Around it there's a subtle elongation, a stretched feature that could be the embryonic version of a bar. In local space, bars and bulges are the calling cards of galaxies that have been around the block, systems that have had billions of years for stars to settle into ordered lanes. Here, that same architecture is showing up less than 1 billion years after the Big Bang. No one expects a cosmic toddler to already have the bones of an adult. Now, let's begin to peel back what that really means. Bars and bulges do not appear overnight. They require gravity to rearrange orbits, gas to sink inward, and time for chaos to cool into structure. Yet JWST's sharp infrared view shows a central region that is not just a random clump. There is a dense core, there are hints of symmetry, and there might even be a primitive bar channeling material straight toward the nucleus, like a conveyor belt feeding a newborn black hole. The spectra deepen the mystery. Instead of a single clean population of freshly minted stars, scientists see signatures of both blazing newborns and slightly older, more evolved stars. That mix means the center has already gone through multiple bursts of activity. Star formation, pause, star formation again. In a universe still catching its breath from the Big Bang, this galaxy's heart has already lived through several cycles. Contrast that with the Milky Way. Our bar and bulge took billions of years to assemble. The bar slowly grew as the disk redistributed angular momentum. The bulge puffed up as stars orbited, collided, and phase mixed. It was a long, slow mission, spread across most of cosmic time. By the end of tonight, you're going to understand why that timeline suddenly looks almost leisurely compared to what JWST has just revealed. Here, the whole process seems compressed into a fraction of the time. Expectation. Early galaxies should be chaotic, clumpy, and unstructured. Reality. This one already shows a central morphology that looks mature. The boundary between young and settled is not where theory placed it. No one predicts that ordered bars and compact bulges can crystallize so fast, yet the data are there, etched into the light. Seeing a galactic core this evolved, this early, forces a hard reset. How fast can gravity sculpt order from chaos? How strongly must dark matter concentrate to pull gas inward so quickly? What kind of cosmic environment drives such an intense front-loaded history, while other galaxies in the same young universe grow more gently? Tonight we're going to follow that question into even deeper territory, because this galaxy's center looks like it has lived a fast, hard life, and the next step is to ask what invisible scaffolding, what dark matter halo and surrounding cosmic web made that possible at all. Tonight, we're going to listen beneath the light, because hidden under those blazing young stars and that overgrown black hole is something even more fundamental. The invisible skeleton that let this galaxy come together so fast. Before we get started, zoom out for a second. In the standard picture, galaxies do not just appear. They condense inside vast halos of dark matter, invisible spheres whose gravity pulls in gas, slows it down, and gives it a place to cool. Those halos are the wells in the cosmic landscape, the basins where gas falls, forms stars, and eventually feeds central black holes. No halo, no galaxy. No deep well, no crowded, blazing core. For the Milky Way, that halo is relatively spread out. The central density is high, but not extreme. Stars in the solar neighborhood orbit calmly, and the inner system grew over billions of years. This new galaxy, by contrast, looks like someone turned the dial all the way up. The central region is tiny, the mass is enormous, and the growth had to be rapid. That combination points to something dramatic in the dark matter underneath. There are two leading ways to get there. One is a halo with an unusually concentrated core, where dark matter piles up steeply toward the center. The other is a rapid series of early mergers, small halos slamming together in the first few 100 million years, dumping their dark matter and gas into one compact region. In both cases, the result is the same. A gravitational pit so deep that gas cannot help but rush inward, ignite, and feed a monster. Now let's begin to connect this to theory. Some models already predict that, at high redshift, dark matter halos should be cuspier than what is inferred in many nearby galaxies. Instead of a gentle plateau, the density spikes, rising sharply toward the centre. A cusp like that makes central collapse easier. Gas falls faster. Star formation ignites earlier. Black hole seeds grow into giants long before planets like those in our solar system even have a chance to assemble. Pattern interrupt. What if the problem is not the halo at all, but the dark matter itself? By the end of tonight, you're going to understand why some scientists are revisiting ideas like self-interacting dark matter, where dark matter particles can nudge and scatter off one another, reshaping the inner profile. Others are looking again at exotic early black hole seeds that might drag dark matter and gas inward, steepening the core from the inside out. No one expects a single compact galaxy to rewrite the dark sector. No one predicts that one nucleus at the edge of the observable universe will expose the blueprint of the entire cosmic web. Yet this galactic heart may be whispering about the true boundary between ordinary matter and the dark scaffolding that holds space together, and the mission now is to listen closely and see if other early centers echo the same hidden design. If that hidden design is real, then a harder question appears at the edge of the frame. Is the Milky Way the template for galaxies, or the oddball that arrived late to the cosmic party? Now, let's begin. To answer that, the mission has to compare our own calm center to the wild hearts JWST is pulling out of the early universe, less than 1 billion years after the Big Bang. At those redshifts, JWST is seeing a very different kind of nucleus. The galaxy that triggered this whole debate hosts an overmassive black hole, punching far above what its total stellar mass would suggest. Its core is ultra-compact, cramming enormous mass into a region far smaller than the Milky Way's bulge. Around it, scientists see a violent starburst, with stars igniting hundreds of times faster than in our solar neighbourhood, embedded in chaotic gas flows and blasted by powerful feedback winds from both supernova and the central engine. This would be shocking as a one-off. But JWST keeps finding cousins. Multiple young galaxies show the same pattern. Black holes already rivaling or exceeding the mass of Sagittarius A, hyperdense cores that look more like cosmic bullets than sprawling bars, and nuclear regions where the gas is so turbulent that neatly ordered orbits do not stand a chance. Designed to reveal faint infrared light from the first systems, this spacecraft has discovered a whole population of extreme centers, as if the early universe preferred its galaxies turned up to 11. Now compare that to home. The Milky Way's black hole is modest on the cosmic scale, quiet most of the time, gently accreting instead of blazing as a quasar. Our bar structures the inner disk in an orderly way, steering gas along predictable lanes rather than shredding it in random turbulence. Star formation near the center is steady, not explosive. By the end of tonight, you're going to understand why some astronomers now suspect that our galaxy might be a late-blooming, quieter type, in a system that once favoured fast, furious growth. Of course, selection effects matter. JWST is especially good at finding bright, active cores whose light can fight through the glare of an expanding universe. No one expects it to easily pick out every sleepy nucleus hiding in the dawn. But even after accounting for that bias, the sheer prevalence of compact, overmassive, feedback-dominated centers is forcing models to bend. No one predicts so many galactic hearts living so hard, so early. So if early galactic centers commonly lived fast and died young, burning fuel, blowing out gas, and locking mass into black holes at record speed, what does that say about long-term fates for galaxies like ours? Are we seeing a quieter evolutionary path that leads to different dark matter structures and different planetary prospects, or just a temporary lull before the Milky Way's own core wakes up? Before we get started on that possibility, the next observation from JWST pushes the question into even more unsettling territory. So here is where your role in this mission really shows up. This is not background noise on a second screen. This is you choosing to sit with a question that reaches from the Milky Way's quiet bar to a violent galactic heart less than 1 billion years after the Big Bang. Most people are content with the simplified textbook diagram: neat spiral, central bulge, one supermassive black hole, end of story. But you're still here while scientists argue over overmassive black holes, dark matter distributions, and chaotic gas flows that refuse to match the standard models. That already puts you in a very small group of people who actually want to understand how the universe really works, not just how it is summarized. Long-form, deep-dive videos like this do not exist by accident. The default in the algorithmic solar system of content is short, fast, and forgettable. No one expects a detailed breakdown of JWST spectra, galactic winds, and early universe timelines to hold attention. No one predicts that viewers will follow a single galactic nucleus from redshift measurements all the way to implications for cosmic evolution. Yet here you are, proving those assumptions wrong in real time. That is why a simple click matters more than it looks. When you like this video, subscribe or share it with someone who loves space. You're not just helping a channel, you're telling the recommendation systems that there is an audience for real science, for missions and measurements, and hard questions about the boundary between theory and observation. Think about what JWST has already delivered. Compact cores that look nothing like our calm center, black holes that seem too massive for their age, starburst rings hidden in infrared light that no previous spacecraft could see. Every time you engage with content that walks through those discoveries carefully, you increase the odds that the next deep field analysis, the next breakdown of a strange galactic center, will be surfaced instead of buried. By the end of tonight, you're going to understand that the path from a single data point to a new model of the cosmos runs straight through communities like this one. People who are willing to pause to replay a diagram of gas inflows and outflows, to let a challenging idea sit for more than 10 seconds before swiping away. So if this journey through space has value for you, consider tapping like, subscribing, or sending it to the one person you know who never stopped asking what lies beyond the edge of the visible universe. Each action is a tiny push, a small solar wind, nudging the algorithmic heliosphere outward, so more curious minds can cross that boundary. Now, let's begin the next leap. With the community question settled for a moment, it is time to zoom out and see where this alien galactic center actually sits in the grand timeline of the universe, from the first stars to the future of galaxies like ours. Now, let's begin. To understand why this distant galactic center is so strange, the timeline itself has to come into focus. Tonight, we're going to compress nearly 14 billion years of cosmic history into a few minutes, just long enough to see where this object lives and why it should not look the way it does. Before we get started, anchor the clock. At time zero, the Big Bang, space itself expands from an incredibly hot, dense state. In the first fractions of a second, the universe is a plasma of particles and radiation. No atoms, no planets, no solar system, just a blinding, roiling field. As it cools over minutes, protons and neutrons lock into light nuclei. Hundreds of thousands of years later, electrons finally bind to those nuclei. That moment is called recombination. Recombination changes everything. The fog of charged particles clears, the cosmic microwave background is released, and for the first time light can travel long distances without being constantly scattered. But there are still no stars, no galaxies, just an expanding sea of dark matter and hydrogen and helium, with tiny ripples in density that gravity will slowly amplify. Those next few 100 million years are the cosmic dark ages. The universe is transparent, but there are no luminous objects to light it up. Gravity works quietly, pulling matter into deeper wells. Dark matter collapses into halos. Gas falls in, cools, and in the densest pockets, the very first stars ignite. They are massive, hot, short-lived, and they flood their surroundings with ultraviolet light. That radiation begins to carve bubbles in the neutral hydrogen between galaxies. This is the era of reionization. The intergalactic medium is no longer a uniform fog. It is a patchwork of ionized cavities growing, overlapping, merging. By the end of tonight, you're going to understand that our JWST target lives right in this transition zone, when the universe is only a few % of its current age. At this stage, the gas between galaxies is still partially neutral, and that has real consequences. Neutral hydrogen is very effective at absorbing certain wavelengths, especially the energetic photons pouring out of young stars and growing black holes. Light from galactic centers has to thread its way through this clumpy medium. Some colors are erased, some emission lines are chopped off. The signal that finally reaches a spacecraft like JWST has already fought its way through a cosmic minefield. The standard prediction is simple. In this young universe, galaxies should be small, irregular, fragile. Their disks are only beginning to settle. Their central bulges are just starting to form. Any black holes in their cores should be modest, still accreting, still climbing toward the masses seen in present-day giants. No one predicts cleanly organized bars, stable rings, or quasar-like engines so early. Yet that is the pattern interrupt. JWST keeps finding compact, bright centers in some of these early systems, with spectra that look less like baby galactic cores and more like scaled-down quasars. The boundary between normal star-forming galaxy and active nucleus is blurred far sooner than scientists expected. Absolutely no one anticipates such powerful engines already switched on, less than 1 billion years after the Big Bang. And this newly discovered galactic heart at the edge of the observable universe may be the most extreme example yet, forcing a rethink of how galaxies and their central black holes grow together. To turn that impossible galactic heart into something scientists can interrogate, JWST has to do more than just stare. It has to build a case, pixel by pixel, photon by photon. Now, let's begin. The raw view is underwhelming, a faint smudge at the edge of the observable universe, barely brighter than the background glow of space. So the mission team doesn't take one picture. They take hundreds, sometimes thousands. Each exposure is short, noisy, and fragile, but stacked together, aligned with sub-pixel precision, and corrected for the spacecraft's tiniest jitters, they reveal structure no one expects to see at that distance. A compact core, a hazy ring, and a ghostly outer halo. Before we get started on the drama in that core, the boring work has to win. Cosmic rays are identified and removed. Detector defects are mapped and subtracted. The faint infrared glow of the telescope's own mirrors is modelled away. What's left is the universe itself pushed to the limit of what this system can reveal. In those deep near-cam images, colour isn't just pretty, it's evidence. Blue-shifted hues hint at young, hot stars. Redder tones betray dust and extreme distance. A tiny, unusually compact knot with the wrong colour for its neighbourhood. That's a prime suspect for an active galactic centre. From that crowded deep field, astronomers have to choose where to spend precious spectroscopy time. They look for galaxies that are small but bright, with colours that suggest intense ionization and rapid star formation, compressed into regions only a few hundred light-years across. By the end of tonight, you're going to understand why those compact, oddly coloured points are treated like crime scenes in need of forensic sweeps. This is where NearSpec enters, like a laboratory scanner for the cosmos. Unlike old missions that could probe only one target at a time, NearSpec can open dozens, even hundreds, of tiny shutters on its micro-shutter array. It can take spectra of the blazing core, the surrounding star-forming ring, and the quieter outer galaxy in a single observation. One exposure, many suspects. The result isn't an image. It's a barcode of a light for each region, stretching from near-infrared wavelengths out toward the red, where the expanding universe has dragged ancient photons. Those barcodes are where the real detective work begins. Every emission line has a preferred temperature, a favourite density, a telltale sensitivity to metals forged in earlier generations of stars. Models are fitted to the spectra, tweaking gas temperature, electron density and metallicity until the synthetic lines match what JWST recorded. If the ratios of oxygen, nitrogen, and hydrogen lines point to extremely hard radiation, scientists infer an actively feeding black hole. If the lines are strong but softer, with signatures of stellar winds and supernova-heated gas, a starburst dominates instead. Prediction meets observation, and the identity of the ionization source is revealed. In that sense, every pixel is a footprint. Every spectral line is a fingerprint. Together they turn a distant point of light into a full crime scene reconstruction of a galactic heart's life story. From its first furious starburst to the moment its central black hole takes control. Those footprints and fingerprints lead to one unavoidable question. How fast did the central monster have to grow to leave marks this deep, this early? When scientists run the numbers, the answer is uncomfortable. It is right at the edge of what standard models can tolerate. Now, let's begin with the simplest version of the problem. Picture a seed black hole forming from the collapse of a massive star, maybe 100 solar masses, sitting in a young galaxy less than 1 billion years after the Big Bang. Feed it continuously at the Eddington limit, the theoretical rate where radiation pressure and gravity balance, and it grows on an exponential clock. The mass doubles roughly every 45 million years. On paper, that sounds generous. A few 100 million years, a handful of doublings, and the seed should bulk up. But count the doublings. To go from 100 solar masses to, say, 10 billion, it needs about 27 doubling times. At 45 million years each, that is over 1.2 billion years of uninterrupted, perfectly tuned accretion. JWST, staring across space and time, is seeing candidates that massive when the universe itself is only 700 or 800 million years old. Expectation versus reality. The math says there is not enough time. The spectra say the black hole is already there. One way out is to start bigger. Instead of a stellar remnant, imagine a direct collapse black hole, a primordial gas cloud, 100,000 to 1 million solar masses that never fragments into stars but collapses straight into a black hole. No one expects that to be common in the local universe. But in the first few 100 million years, under intense ultraviolet backgrounds and chaotic inflows, it might happen. JWST's discovery of compact, hyperdense galactic cores with overmassive black holes lends weight to this scenario. If the seeds are huge, the growth clock starts much closer to the finish line. Another escape hatch is to cheat the limit. Super Eddington accretion, where gas funnels in faster than the textbook maximum, can occur if inflowing material is clumpy, anisotropic, or buried in thick funnels that trap radiation. For short bursts, the black hole can grow far more rapidly. Those episodes would leave signatures: extremely blue continua, powerful winds, broad emission lines pushed and skewed by outflows that rival the escape velocities of entire planets and solar systems. Of course, every measurement hides uncertainties. Maybe the mass is overestimated because the gas dynamics are more complex than the models assume. Maybe gravitational lensing is quietly magnifying the galaxy, making the black hole look heavier than it is. Scientists have chased all of those possibilities, dialing every parameter to conservative values. Even then, the growth timeline is strained almost to breaking. Tonight, we're going to follow that strain to its logical conclusion. By the end of tonight, you're going to understand why this single galactic centre hints that nature has a fast track for building monsters, and why the next object JWST has discovered may push that boundary even further. So here's the twist. All those growth curves that barely fit inside 1 billion years. In this galaxy, the centre behaves as if someone hit fast forward on the remote and then snapped the button off. The Milky Way took its time. Over billions of years, a stellar bar slowly funneled gas inward, the central bulge puffed up, and the black hole at the heart of the system sipped matter in intermittent episodes. Quiet phases, active phases, long pauses. In contrast, the JWST nucleus looks like that entire multi-billion-year movie compressed into a brutal high-intensity montage. No one expects a bar-dominated, orderly core. Scientists instead see a compact blazing knot where everything seems to be happening at once. Why does the early universe run so hot? High gas fractions are the first clue. Back then, galaxies were drenched in cold hydrogen, not the thin, recycled leftovers the Milky Way plays with today. That gas doesn't drift politely. Gravitational instabilities, spiral shocks, and clumpy disks drive it inward like a cosmic landslide. Add in a merger rate far higher than in the modern universe, and every close encounter becomes a mission to shove more fuel toward the center. Tonight, we're going to treat those mergers as delivery service with no speed limit. Two young galaxies collide, their stars mostly pass through, but their gas slams together, shocks, and loses angular momentum. In a few tens of millions of years, a blink compared to the Milky Way's timeline, vast reservoirs of gas pile up in the inner few hundred light years. Where our solar neighborhood orbits in a relatively calm disk, this galaxy's core is a storm front. When that much mass reaches the center that quickly, feedback loops ignite. Dense gas clouds fragment, triggering rapid starbursts that can form thousands of solar masses of stars per year. Supernovae and stellar winds then stir and compress the remaining gas, pushing even more of it toward the black hole. Runaway central growth becomes almost unavoidable. The core gets denser, the starburst gets brighter, and the black hole briefly grows faster than the rest of the galaxy can keep up. Now, let's begin a thought experiment. What happens after the binge? One path leads toward a Milky Way, like future. Over time, outflows from the black hole and exploding stars clear out the inner gas. The merger rate drops, and a bar may eventually emerge to manage the remaining inflow more gently. The galaxy settles, builds a stable disk, and its overgrown black hole gradually waits while the stellar mass catches up. The other path is harsher. The central engine blows so hard that it ejects or heats most of the remaining gas. Star formation crashes. The galaxy stops growing and becomes a compact, quenched relic, a dense fossil of its own violent youth, still orbiting quietly in space while younger systems keep evolving around it. By the end of tonight, you're going to understand why these fast-forwarded cores are more than curiosities. They are time-lapse mirrors. By reading their spectra and mapping their winds, scientists are watching, in compressed form, the adolescence our own galactic center has long since left behind, and testing which future the Milky Way might have narrowly avoided. That adolescence leaves a fossil in the numbers. In the nearby universe, where galaxies have had billions of years to settle down, there is a tight pattern. The heavier the central bulge of stars, the heavier the black hole hiding at its core. Not a one-to-one match, but close. On average, the black hole weighs in at about 0.1% of the bulge. Change the bulge, and you change the heart. This correlation is the backbone of coevolution. It tells scientists that the core and the city around it are talking. As the black hole feeds, it launches winds and jets that heat and stir the surrounding gas, sometimes blowing it out of the galaxy, sometimes compressing it into new stars. Feedback, growth and regulation, locked together. By the end of tonight, you're going to understand why so many models assume that if you know the bulge, you can guess the black hole. Then JWST points at this faint system less than 1 billion years after the Big Bang, and the numbers refuse to cooperate. The stellar body is still modest, a compact, rapidly assembling galaxy. But the central black hole? It looks huge, rivaling or exceeding the mass of the Milky Way's own core engine, even though the host galaxy has only built a fraction of our bulge. On the usual local plot of black hole mass versus bulge mass, this object does not sit on the line. It floats well above it. Expectation. Young galaxies should still be climbing toward the relation seen nearby. Reality, this one has a galactic heart that has already outgrown its body. No one expects such an overmassive core so early. No one predicts such a mismatch if coevolution is perfectly synchronized. And absolutely no one anticipates that multiple JWST targets would hint that this is not a lone outlier, but part of a population. Now let's begin to unpack what that means. One extreme scenario says the black hole wins the race. Seeded by a massive collapse, it grows first and fast, swallowing gas at near the theoretical limit while the young system is still chaotic. Its radiation and winds then slam into the surrounding medium, carving out cavities, quenching some star formation, and forcing the galaxy to catch up later, if it can. The opposite picture puts the galaxy first. In that view, dense clumps of gas merge, stars form, a bulge assembles, and only then does enough material trickle inward to feed and inflate the central black hole. Growth is more measured, more balanced, closer to what is inferred for many present-day systems. JWST's overmassive cores suggest both tracks might be real. Some galaxies may pass through an early black hole-dominated phase, where the central engine sets the pace and the stellar city struggles to keep up. Others may follow a calmer, more synchronized path, with feedback acting like a thermostat rather than a blowtorch. The Milky Way, with its relatively modest central black hole and sprawling disk, may be the poster child for that slower route. So which timeline did our own system follow? Is the Milky Way the product of a long-negotiated truce between stars and central gravity, while this distant galaxy represents a front-loaded high-risk growth strategy written into the universe's first billion years? If that was the big-picture strategy, then the real shock comes when you zoom in. Now let's begin. Take those abstract curves and growth rates and dive straight into the central few hundred light-years of this JWST galaxy. Tonight, we're going to stand, at least in imagination, inside a galactic heart that never learned the meaning of quiet. Every direction is light. Not the gentle glow you see from the Milky Way center on long exposure images, but blinding radiation that would vaporize an unshielded spacecraft long before it could complete its mission. Dense star clusters pack the core, thousands of suns crammed into volumes where, in our solar neighborhood, you might find just a handful. Between them, rivers of gas slam together at hundreds of kilometers per second. Where those flows collide, shock fronts flare into existence, walls of compressed plasma that flash in X-rays and ultraviolet, then cool just enough to collapse again. In those collapsing ridges, new stars ignite almost as fast as the gas can fall. Massive, short-lived giants dominate the scene, blue-white and furious. They burn through their fuel in a few million years, then die with almost no warning. No one predicts a peaceful night under such a sky. Supernova explosions go off in rapid succession, overlapping shock waves like overlapping thunderclaps, carving hot, empty bubbles in the surrounding gas while narrow filaments between those cavities are squeezed into even denser threads where the next generation of stars will form. At the exact center, the real engine roars. The overmassive black hole JWST revealed is wrapped in an accretion disk so bright it outshines entire swarms of planets and stars around it. As gas spirals inward, friction heats it to tens of millions of degrees, unleashing high-energy photons that tear electrons off atoms and turn the inner core into a sea of ionized wind. Along the black hole's spin axis, twin jets punch outward, drilling channels through the surrounding medium, evacuating tunnels that can stretch for thousands of light-years. Compared to this, the Milky Way's core feels almost sedate. Our solar system orbits far out in the disk, and even a star parked much closer to Sagittarius A would face hazards, radiation bursts, gravitational nudges, occasional supernova, but not this relentless overlapping cascade of cataclysms. Here, the boundary between star formation and star destruction is sharp but rarely crossed. There, it is crossed every single moment. By the end of tonight, you're going to understand why any hypothetical planetary system born near that early galactic centre would be living on borrowed time. Constant blasts of high-energy light, shock waves sweeping through like cosmic hurricanes, jets that can strip atmospheres clean. This is a heart built for transformation, not for life. So if planets cannot survive here for long, what does that say about where the first truly stable homes for life could appear in a universe that begins this violently? So if planets cannot survive long in those chaotic cores, the next question hits hard. Where did the universe actually build its first long-term neighbourhoods? To answer that, you have to zoom out from a single doomed orbit and look at how entire galaxies were making stars when space was less than 1 billion years old. Tonight, we're going to follow that trail straight into the crowded hearts of young galaxies. The expectation is simple. Spread star formation gently across a galaxy, like the Milky Way's spiral arms, and you get a wide range of environments, from calm to chaotic. The reality JWST is revealing is very different. In many early systems, the light is packed into the centre. Star formation is not politely distributed. It's piled into a compact core where gas, gravity, and radiation are all trying to occupy the same tiny region of space. That means the universe's first generations of stars may have been born shoulder to shoulder in environments far more crowded than the solar neighbourhood you know. Imagine a stellar nursery where the nearest newborn sun is not a few light years away, but a fraction of a light year. Where every direction you look, massive stars are turning on, blasting winds and exploding in rapid succession. No one expects a calm pastoral galaxy to emerge from that. In regions that dense, the rules of star formation shift. The initial mass function, the statistical recipe that says how many small stars versus big ones you get, depends on temperature, turbulence, and pressure. Pack gas into a hot, turbulent core, and the physics may favour more massive stars. They ignite quickly, burn furiously, and die young. By the end of tonight, you're going to understand why that matters for everything that comes after. Those massive stars are chemical engines. Their winds and supernovae forge and fling heavy elements, carbon, oxygen, silicon, iron, back into the surrounding gas. If the starburst is concentrated near the galactic centre, that enrichment is like a rapid-fire recycling plant operating right at the core. One generation explodes, the next forms almost immediately from gas that is already seeded with metals. Here's the pattern interrupt. Early galaxies are supposed to be pristine, with almost no heavy elements. Yet JWST is finding pockets of surprisingly metal-rich gas less than 1 billion years after the Big Bang. That looks contradictory, until you remember these hyperdense cores. A few 100 million years of centrally focused starbursts and supernovae can push the metallicity of the inner regions far ahead of the outskirts. So when scientists see a young galaxy whose central gas looks chemically mature, while its outer regions still appear primitive, this kind of nucleus star formation offers a natural explanation. The boundary between early and evolved is not the same everywhere inside a single system. No one predicts that the behaviour of galactic hearts in the first billion years would ripple outward into such large consequences, yet it does. The timing of planet formation, the availability of elements like silicon and oxygen, even the chances for life to assemble complex chemistry, all of it is shaped by how violently and how centrally those first stars were born. So when that early galactic heart detonates into a frenzy of stars and gas, another question appears at the centre like a gravity well. Are we looking at a star-bursting core, or are we watching the opening act of a quasar? Tonight we're going to push right up against that boundary and see how thin it really is. Quasars are the drama kings of the cosmos. They are the most luminous active galactic nuclei, powered by supermassive black holes swallowing matter at furious rates. As gas spirals inward, it heats to millions of degrees, blasting out radiation that can outshine every star in the host galaxy combined. From across the observable universe, a single quasar can look brighter than entire clusters of galaxies. That is the extreme end of what a galactic centre can become. The JWST galaxy at the edge of the universe does not quite reach that level. Its total luminosity is lower, its power output more modest than the monsters catalogued by earlier missions. But its core carries familiar quasar signatures. There is a compact, brilliant nucleus. There are strong, broadened emission lines in the spectra, the fingerprints of fast, hot gas swirling around something very massive. There is evidence for winds being driven out of the centre, pushing against the surrounding system. So what is it? Too bright and too concentrated to be a calmer Milky Way style bulge. Not quite luminous enough to join the ranks of the classic quasars lighting up the same epoch. This is where the idea of mini-quasars comes in. Many scientists now suspect that in the first billion years, a huge fraction of galaxies passed through a phase where their centres were highly active, but not yet fully dialed up to quasar levels. In that picture, a compact, star-bursting core like this is not an anomaly. It is developmental stage. Gas is pouring inward, feeding both rapid star formation and a growing black hole. The nucleus is bright, the feedback is violent, but the accretion rate has not yet saturated into the blazing quasar regime. Designed on paper, these phases looked rare and short. JWST is showing they might be common and long-lived. By the end of tonight, you're going to understand why that matters. If mini-quasar phases are widespread, they could be the missing bridge between quiet, rotating disks and the fully lit quasars already known at similar redshifts. Predictions said quasars should appear only after galaxies assembled most of their mass. Observation now hints that compact, overachieving cores may come first, preheating and reshaping their planet's future environments. No one expects a single galaxy to rewrite the history of galactic evolution. No one predicts that a slightly underluminous nucleus would expose an entire hidden population. Yet, that is what this object threatens to do. By catching these intermediate states in the act, JWST is filling in the missing frames of how galactic hearts evolve, from chaos to quiescence, and setting up a new question. Just how many early galaxies hid their own mini-quasar engines from earlier generations of telescopes? So when astronomers say this galaxy lives near the edge of the universe, they are not claiming space just stops there like a painted backdrop. They are talking about the edge of the observable universe, the farthest distances from which light has had time to reach our telescopes since the Big Bang. Before we get started on what that really means, picture this. The universe is about 13.8 billion years old. But because space itself has expanded, the most distant galaxies we can see today are not 13.8 billion light-years away. Their light has been stretched, their distances have grown, and the true radius of the observable universe is closer to 46 billion light-years. Tonight we're going to stand right up against that observational boundary. The key is redshift. As space expands, wavelengths of light from distant galaxies are stretched into the infrared. JWST was built to live in that stretched-out universe. Its instruments like NIRCam and NIRSpec target galaxies whose light left them when the cosmos was only a few 100 million years old. By the end of tonight, you're going to understand that when scientists quote a redshift, they're really quoting a look-back time, a timestamp on the universe itself. This particular galactic centre sits at an extreme redshift, in an era less than 1 billion years after the Big Bang. Not quite at the absolute limit JWST can reach, but close enough that each photon has been travelling for over 13 billion years. Designed to study nearby planets and faint solar system objects? No. This spacecraft was designed from the start to turn those ancient reddened whispers into detailed spectra. And what it has discovered out there does not line up with the playbook. Here is the deeper problem. Most theoretical models of galaxy evolution are calibrated on the local universe. Nearby spirals, nearby ellipticals, the calm, bar-dominated centre of the Milky Way. From those, simulations are run backward in time, rewinding the cosmic movie to predict what young galaxies should look like. Smooth growth, Gradual feeding of central black holes, a tidy sequence. Then JWST points at the edge of the observable universe and finds compact, hyperdense cores and overmassive black holes already in place. The boundary between prediction and observation snaps. The mass of the central object is too high. The star formation near the core is too intense. The gas flows are too chaotic. No one expects a mini quasar engine to be this mature, this fast. When a galactic centre near the observational edge refuses to match those extrapolations, it is a warning light on the dashboard. Something fundamental is missing, either in how black holes grow, how dark matter assembles, or how early gas collapses under gravity's pull. Now, let's begin to treat this not as one weird outlier, but as a probe of the line between what computers can simulate and what the universe actually did. Because if this galaxy is not alone, the next object's JWST reveals just beyond it may force a far more radical rewrite than anyone predicts. So pause the simulations for a moment and flip the experiment. Instead of asking why that distant galaxy is so extreme, ask this. What if the Milky Way had grown up like that? Before we get started with more data and spectra, step into an alternate solar system, inside a very different home galaxy. In this version of reality, the central black hole does not take the slow, patient route. Within the first billion years, it races to hundreds of millions of solar masses. It grows fast, it grows hot, and it grows loud. The core becomes a quasar heart, flooding space with radiation while the surrounding young disk is still trying to assemble. Tonight, we're going to stand on an imaginary Earth inside that galaxy and look up. The night sky is not dominated by a soft, hazy Milky Way band. The central bulge blazes. Even from tens of thousands of light years away, the galactic center is a hard, brilliant knot, brighter than any region you see today. Dust near the core glows in infrared, gas clouds fluoresce, and the contrast between the quiet outer disk and the raging heart is impossible to miss. The difference is not just brightness. A supercharged nucleus drives winds. Powerful outflows blast out of the core, carving cones through the surrounding gas, pushing on the boundary between bulge and disk. Those winds reshape where new stars can form. Some directions are stripped clean, others are compressed into dense rings that ignite starbursts. In that history, the Milky Way's spiral structure might never settle into the graceful extended arms known today. The inner disk could be thicker, more chaotic, with short broken arms rather than long symmetric spirals. A violent early feedback phase might heat the gas so much that star formation shuts down in the inner regions for hundreds of millions of years, then restarts in waves. Even the population of satellite galaxies might change. Strong outflows from the core can blow metals and gas into the halo, pre-enriching small companions or stripping them bare. Some dwarfs could light up early and then fade, while others never get the fuel to build many stars at all. The architecture of the whole system tilts around that overgrown center. Now bring life into this alternate mission. A more active core means more high-energy radiation, more jets, more flares. Close to the center, planets might face frequent sterilizing events. But far out in the disk, tens of thousands of light-years away, the thick gas and dust of the galactic plane still provide shielding. Habitable zones might migrate outward, but they do not vanish. By the end of tonight, you're going to understand that this isn't just fantasy. JWST is now revealing real galaxies that took this path, with overmassive black holes and compact blazing cores less than 1 billion years after the Big Bang. No one expects our quiet, bar-dominated center to be the template. No one predicts that the Milky Way is the rule. The next question is why our own galaxy avoided that fate, and what that says about the range of possible cosmic histories JWST is about to uncover. So if our galaxy is not the rule, the obvious question is how many alien hearts like this are out there? How many young galaxies grew up with raging overmassive cores instead of the calm bar-dominated center we orbit today? Tonight, we're going to zoom out from that single extreme nucleus and look at the statistics JWST is starting to build. Designed to map the infinite universe, it keeps stumbling on something no one expects: a surprising number of massive compact galaxies and active galactic nuclei less than 1 billion years after the Big Bang. Tiny red smudges in deep fields turn out, under NIRCam and NIRSpec, to be dense stellar cities wrapped around black holes that already rival or exceed the Milky Ways. Predictions said the early universe should be dominated by small, puffy, gradually assembling systems. Observation is giving something else. In survey after survey, from Sears to JDs to Premier, scientists see galaxies at redshift 6, 8, even beyond 10, with stellar masses of tens of billions of suns, half-light radii only a few hundred parsecs across, and emission lines screaming that their cores are furiously accreting. The boundary between normal starburst and buried quasar blurs. But there is a catch. These first catalogues are small and biased toward the brightest, most compact objects, because those are the ones a finite mission can see cleanly at the edge of the observable universe. Selection effects matter. A face-on dust-free nucleus looks different to JWST than a choked edge-on one. A galaxy caught in a brief flare of accretion will be promoted into the sample, while a quieter twin just below the detection limit vanishes into the noise. By the end of tonight, you're going to understand why scientists are both excited and cautious when they count these monsters. Even with those caveats, the trend is hard to ignore. Compared to pre-JWST models, there are more early extremes than expected. More compact cores, more candidates for overmassive black holes, more galaxies whose central regions look dynamically mature, while the surrounding cosmic web is barely assembled. No one predicts that kind of head start. That is why whole JWST programs are now pivoting to the centers on purpose. Deep mosaics don't just tally galaxy numbers, they dissect inner kiloparsecs. Integral field spectroscopy maps how gas flows, where the winds from young stars and accreting black holes slam into the surrounding medium, and how fast these cores are growing. Targeted follow-ups on the brightest high-redshift quasars probe their host galaxies, weighing both the black hole and the stellar body to see who is winning the growth race. And yet there is a sense that this is only the tip of the iceberg. Absolutely no one anticipates that the first year of data has already revealed the full population. For every blazing nucleus that clears the detection threshold, there may be 10 more smothered in dust, or simply too faint in the infrared for this spacecraft to register. The universe might be littered with half-grown monsters whose light never quite reaches us. If that is true, then the quiet, orderly centre of the solar system's home galaxy is not just pleasant. It is rare, a luxury. In a cosmos that appears to have started with a violent top-heavy rush towards central dominance, living next to a relatively modest black hole in a bar-stabilized disk might be the exception. The next step is to ask what that rarity means for the planets, and for the long-term habitability of regions orbiting calmer galactic hearts like ours. A calm galactic neighborhood is a luxury, but a luxury does not rewrite physics on its own. To see what these extreme early cores say about dark matter, the first rule is simple. Remember what JWST actually measures. It sees light, starlight, gas emission, dust glowing in infrared. It does not see the invisible mass itself. So when scientists talk about dark matter in these distant systems, they are working through a chain. Light traces stars and gas. Stars and gas respond to gravity. Gravity, in turn, is dominated by whatever mass is there, including the dark component. Every conclusion about dark matter is indirect, model-dependent and tied to assumptions about how the whole system evolves. Tonight, we're going to stand right at that boundary between what is measured and what is inferred, because the way dark matter is arranged in a halo can change the entire story of how a galaxy's heart forms. Pack more dark matter into the central region, and gravity deepens the potential well. Gas falls in faster, cores get denser, spread the dark matter out, and collapse is slower, more diffuse, less like a cosmic high-rise, and more like a sprawling suburb. This is where simulations become the testbed. In standard cold, dark matter, halos grow hierarchically, merging and accreting material over time. Some simulations using that very ordinary recipe can, under the right conditions, produce compact, massive cores early on. Rapid gas cooling, a burst of star formation, and strong inflows are enough. In other runs, the same cold, dark matter framework struggles, unless the model includes extra twists, very early mergers, tuned feedback from supernovae and black holes, or altered prescriptions for how gas turns into stars. Prediction meets observation here, and the match is not yet perfect. No one expects every simulation to land exactly on the first JWST data release. No one predicts that a single run will capture every overmassive black hole and every ultra-dense core. But absolutely no one anticipates that standard cold dark matter is ruled out by a handful of bright distant points of light. There are, of course, alternative ideas. Warm dark matter that erases small-scale structure, self-interacting dark matter that can redistribute mass in the center of halos, exotic models where the dark sector has its own forces and cooling. In principle, each of these could sculpt different central densities, changing how quickly those early galactic hearts ignite. By the end of tonight, you're going to understand why that sounds tempting, but dangerous. Because right now, the data are not decisive enough to crown a winner. JWST is showing what is possible, not yet what is mandatory. These compact centers are new laboratories, where gravity, gas physics, and dark matter all intersect in regimes beyond anything the local universe can offer. The next step is to ask what happens when planets form under those conditions, and whether life can survive in the glare of such a different kind of galactic heart. So if early galactic centers are this alien, where do we go from here? The next phase is simple to describe and hard to execute. Push JWST to the absolute edge of space and time and see whether these monsters are rare exceptions or the rule. Tonight, we're going to follow that roadmap into the next few observing cycles. The first move is to go higher in redshift and lower in drama. Up to now, the loudest systems have grabbed the headlines: blazing quasars, hypercompact starbursts, black holes punching far above their expected weight. But to understand a system, scientists have to study the quiet cases too. Several upcoming JWST programs are targeting extremely faint smudges at redshifts beyond 10, galaxies less than 500 million years after the Big Bang, chosen precisely because they look boring. If those galaxies hide dense, efficient cores as well, then the entire early universe may have grown from a different playbook. At the same time, observers are going back to the known extremes with sharper tools. Early spectra of these cores were often quick reconnaissance passes, enough to flag a huge black hole, a wild star formation rate, a chaotic wind. The next step is deep, high-resolution spectroscopy with NIR SPEC and MIRI, staring for tens of hours at a single nucleus. That lets the mission measure subtle line shapes and velocity shifts, pinning down black hole masses, mapping how gas orbits, and reconstructing when bursts of stars turned on and off. Expect maps where every pixel is a speed, a temperature, a chemical fingerprint. But JWST alone cannot solve this. The boundary between a complete picture and a beautiful illusion is thin, and other observatories will decide which side we land on. ALMA will trace the cold molecular gas feeding these cores, revealing whether they are sipping from thin filaments or gorging on thick rotating disks. Future X-ray missions will hunt for the hardest radiation from accretion, the unmistakable signature of matter falling into deep gravity wells. When infrared, millimeter, and X-ray data all point to the same violent heart, the case becomes unambiguous. While the spacecraft stare, theorists are racing to catch up. No one expects simulations built for gentle Milky Way, like bulges to reproduce a billion solar mass black hole in a baby galaxy. No one predicts compact star-forming rings that convert gas to stars with near-perfect efficiency. Yet that is what JWST has discovered. So teams are rewriting their codes, cranking up early gas inflows, changing how black holes seed and merge, letting feedback carve and compress the central regions. By the end of tonight, you're going to understand that these virtual universes are not just movies. They are prediction engines JWST can test line by line. Now, let's begin to look ahead a few years. Either the next wave of data will gently bend our existing models until they pass through every new point, or the tension will snap. If these alien centers refuse to be tamed, absolutely no one anticipates how deep the rewrite of galaxy evolution may have to go. If those alien cores refuse to fit, then the whole idea of what a normal galactic center looks like has to move. Not a tiny adjustment, a full redraw of the mental map you carry of how galaxies grow their hearts across cosmic time. Before we get started, remember the old picture. In textbooks and simulations, galaxies follow a smooth arc, small messy clumps in the early universe, slowly merging and settling down into big ordered disks with calm, rounded bulges. The center is supposed to be the quiet grown-up in the room, where stars orbit in stable paths, and the central black hole grows politely, always a modest fraction of the galaxy's mass. That expectation runs deep. Star formation is meant to start chaotic and then decline. Gas is meant to cool, sink, and organize. The central bulge, in this story, is the end state of a long negotiation between gravity, gas, and time, not a battlefield. The Milky Way's bar and relatively gentle central wind became the template, designed for order, destined for calm. JWST is shredding that script. Tonight, we're going to stand next to those early galactic centers and watch them misbehave. At redshifts beyond 10, less than 500 to 700 million years after the Big Bang, scientists are seeing compact, hyperdense cores where the central regions are so bright and so small that the whole galaxy looks like a single point. Spectra show furious starbursts, gas screaming in at hundreds of kilometers per second, and black holes already weighing as much as or more than the Milky Ways, inside galaxies that are still cosmic toddlers. Prediction versus observation could not be sharper. The standard models said black holes should lag behind, growing slowly as the host galaxy builds its stars. JWST discovered case after case where the black hole is ahead of schedule, temporarily outpacing the galaxy that feeds it. No one predicts a mini-quasar blazing in a system that small. Yet there it is, a central engine punching out radiation, driving winds that threaten to blow the galaxy's own fuel into intergalactic space. So the mental model has to change. Think in phases, not a single smooth curve. First, a chaotic starburst core phase, where gas floods the center and ignites dense rings of star formation around a seed black hole. Then, a mini-quasar state, where the black hole's growth spikes and feedback becomes violent, launching jets and winds that reshape the inner few thousand light-years. Finally, a feedback-regulated quieting, where the outflows heat and stir the remaining gas until the core settles into something more like the Milky Way's bar and bulge. Pattern interrupt. What if the Milky Way is not the rule, but the survivor of a very specific path through those phases? Our center, with its modestly active black hole and controlled star formation, may be just one endpoint on a wide spectrum. Other galaxies might stall in the starburst stage. Some could burn out early under their own feedback. By the end of tonight, you're going to understand that normal now has to stretch. It must cover both our relatively calm, bar-dominated core and those compact, overgrown, violently active hearts at the edge of the observable universe. The new boundary of what counts as typical is not a single example. It is the entire family of galactic centers, from quiet to quasar, all sharing the same cosmic stage. Now, let's begin to ask what that means for the future of our own galaxy and for the next generation of missions that will try to watch these phases unfold in real time. Now let's begin to bring those extreme edge-of-time hearts back to something familiar. Picture this. You step outside on a clear night, far from city lights. Overhead, the Milky Way arches across the sky, a pale river of stars. Near the centre there's a brighter swelling, a hazy bulge. To the naked eye it looks calm, serene. But you're staring into the quiet aftermath of ancient violence. That glow is not just pretty space wallpaper, it is a fossil record. Long before the solar system formed, waves of starbirth and stardeath swept through that central bulge. Supernovae ripped apart giant stars, black holes shredded wayward gas clouds, shock waves ploughed through the galactic core like a storm front. JWST is now seeing versions of that chaos frozen in time, in galaxies less than 1 billion years old, when those processes ran hotter, faster, and far more extreme than what the Milky Way shows today. Tonight we're going to connect that distant fury to something uncomfortably close. Your own body, the calcium in your bones, the iron in your blood, the oxygen in your lungs, the silicon in the planets under your feet. None of it emerged from the Big Bang. The early universe made hydrogen, helium, and a trace of lithium. Everything heavier was forged later, inside stars that lived hard and died violently, often in crowded galactic centres like the ones JWST has just discovered at the cosmic boundary. In those compact cores, rapid star formation and supermassive black holes act together like a cosmic engine. Stars fuse light elements into heavier ones. Supernovae blast those elements into the surrounding gas. Black holes stir and heat that gas with outflows and wind. Over millions of years, that enriched material drifts outward, mixes into the wider galaxy, and eventually condenses into new generations of stars and planets. By the end of tonight, you're going to understand that some of the atoms composing you may have passed through environments that once resembled those distant turbulent hearts. This is where context matters. The Milky Way's centre is comparatively quiet now. No one predicts it has always been so gentle, yet compared to the hyperdense, overmassive black hole systems at high redshift, our galaxy looks like it took a less brutal path. JWST lets scientists compare these different galactic histories directly. What did our galaxy go through? How many quasar-like phases did it survive? And what catastrophic feedback phases did it somehow avoid, allowing a stable disk, long-lived planets, and a calm solar system to emerge far from the core? There is an irony here that absolutely no one anticipates at first glance. To learn intimate details about the forces that shape this quiet patch of sky, observers have to look to the very edge of the observable universe. The farther out in space they look, the further back in time they see, until those faint smudges become snapshots of what galactic centres used to be, including what ours may once have resembled. So when you stand under that dark sky, you're not just seeing a backdrop, you're seeing the endpoint of a story JWST is now reading from the beginning. The mission has turned galactic centres from a single, local example into an entire family of possible hearts, revealing how black holes, stars, and gas co-evolve across cosmic time. Before we get started on the final synthesis, keep one question in mind. If our picture of galactic cores has changed this much in just a few years, what unseen phase of our own galaxy's future might still be hiding in the data? So if our own core might be hiding a wilder past, what does that say about the very idea of a galactic centre? Tonight, we're going to rebuild that concept from the ground up, because JWST has made one thing painfully clear. The Milky Way is not the template, it's just one example. Now, let's begin. When astronomers say galactic centre, they used to picture something like home, a supermassive black hole in the middle, wrapped in a dense stellar bulge, embedded in lanes of gas and dust, with a bar of stars quietly funneling material inward. A location, a point on a map. but JWST's infrared vision into deep space has turned that tidy sketch into a layered engine, with distinct components that can appear, evolve, and even vanish on different schedules. At the heart sits the central black hole, the anchor of the system. Around it, a compact stellar core or bulge, where stars crowd together thousands of times more densely than near the Sun. Threaded through that is gas and dust, clumpy, turbulent, often shaped into spirals, rings, or bars that act like conveyor belts feeding the core. In some galaxies, JWST resolves tight starburst rings only a few hundred light-years wide, blazing with newborn stars. In others, elongated bars drive gas inward, while powerful winds from the nucleus blow it back out again. The surprise is the order. Classical models assumed the bulge and dark matter halo assembled first, then the black hole slowly grew as gas drifted in. Prediction versus observation, JWST is now seeing overmassive black holes less than 1 billion years after the Big Bang, sitting in relatively modest galaxies that haven't had time to build Milky Way style bulges. No one predicts a central engine that big, that early, in a system that small, yet the spectra don't lie. Some of these young nuclei look like the black hole turned on first, and the surrounding city of stars is still rushing to catch up. By the end of tonight, you're going to understand that a centre is not a calm dot. It's a dynamic engine. In one epoch it can be near dormant with only weak accretion and a quiet stellar population, like our present core. In another, it erupts into a quasar, driving winds that punch holes in the surrounding gas and set a hard boundary on future star formation. The same coordinates in space can host completely different behaviours as fuel supply, mergers and environment change. This redefinition matters. When a faint smudge near the edge of the observable universe lights up in JWST's NIRCam images, scientists can no longer assume its centre is a scaled-down Milky Way. It might be a compact, ultra-dense knot of stars, a naked black hole blazing in X-rays, or a chaotic ring where feedback is rewriting the galaxy in real time. The term galactic centre now encodes an evolutionary state, not just a position. No one expects a single phrase to stretch this far, but here we are. Thanks to this mission, Galactic Centre now conjures not just our relatively calm core, but a whole zoo of alien hearts, beating at different cosmic ages, each marking a different chapter in how galaxies grow, burn, and transform across the history of the universe. But for all that, there's a quiet truth sitting underneath these dramatic alien hearts. There is still a lot that no one understands. The first unknown is baked right into the centre. What were the original black hole seeds in these young galaxies? Are we looking at the descendants of massive short-lived stars that collapsed early, a few hundred solar masses at most, slowly fed by gas over time? Or did some regions of the early universe skip stars entirely and collapse straight into black holes tens or even hundreds of thousands of solar masses across? The seed mass sets the whole growth curve, yet JWST is catching these monsters mid-story, not at page 1. Then there is the question of how the gas actually gets in. The images show chaotic structures, clumpy spirals, compact cores, violent winds blasting outward. But the detailed inflow mechanisms remain blurry. Are cold streams from the cosmic web funneling material directly into the centre? Are mergers doing the heavy lifting, shaking galaxies and driving gas inward? Or are internal instabilities, bars and rings we can barely resolve, quietly steering matter toward the heart while star formation tries to blow it back out? That leads to a deeper puzzle. How common are these overmassive cores really? Is JWST seeing rare extremes because the mission is staring at the brightest, most dramatic examples near the edge of the observable universe? Or is the Milky Way's relatively modest centre the oddball in the cosmic sample? Tonight, we're going to keep that question open, because the statistics are still thin. A handful of spectacular detections does not yet tell the full population story. Part of the problem is brutally practical. Even JWST has limited spatial resolution at these distances. What looks like a single blazing point can actually hide a crowded neighbourhood of stars, gas and dust stacked along the same line of sight. Emission lines from starburst regions and from the active black hole overlap in the spectra. Untangling how much light comes from newborn stars and how much from the accretion disk is like trying to separate two songs played through one tiny speaker at the far end of the solar system. So different teams build different models. One group fits the data with a relatively modest black hole plus an extreme starburst. Another uses a heavier black hole and less star formation. Sometimes both interpretations match the same measurements within the errors. Prediction versus observation collapses into a frustrating tie. No one predicts this to be easy, but absolutely no one anticipates just how ambiguous high redshift galaxies can be when viewed through a narrow spectral window. Here is the crucial part. Science does not progress by smoothing over these contradictions. It advances by staring straight at them. JWST was designed to push us into this uncomfortable territory, to move the boundary between known and mysterious right into the middle of what we thought were settled models of galaxy evolution. So before we get started on neat answers, it helps to see these gaps for what they really are. Not failures. Invitations. Invitations to deeper surveys, to future missions that will map gas motions in even finer detail, to new theories that can handle black holes and galaxies growing in lockstep or wildly out of sync. By the end of tonight, you're going to understand that every uncertainty in these alien centers is also an open door to new ideas, and for some viewers, maybe a future career chasing how galactic hearts first learned to beat. Now, let's begin tying those alien galactic hearts to a story you already know. The moment humanity first walked up to a cosmic boundary and discovered it was nothing like the textbooks. Before we get started with Webb at the edge of the universe, think back to Voyager at the edge of the solar system. Two aging spacecraft running on dwindling power, drifting toward a line no one could see. The original plan was modest: map the giant planets, then fade into the dark. No one expects a 5-year mission to redraw the architecture of the entire solar system. No one predicts that when Voyager finally reaches the termination shock and the heliopause, the boundary will be farther out, stranger in shape, and more dynamic than generations of scientists had argued on paper. The solar wind, that thin outflow of charged particles, does not simply taper off. It slams into the interstellar medium, piles up, slows down, and heats. Voyager discovered the edge of our system is not a clean bubble wall, but a wrinkled, shifting frontier. The magnetic field twists. The particle densities jump in ways absolutely no one anticipates. What looked like a neat diagram becomes a stormy coastline. Now fast forward that same pattern to a much larger scale. JWST is Voyager's spiritual cousin, but instead of cruising outward through space, it looks outward through time. Its infrared eyes cut through cosmic dust and expansion, all the way to galaxies less than 1 billion years after the Big Bang. Where Voyager redefined the edge of the heliosphere, Webb is redefining the edge of the observable universe. Models said those first galactic centers should be small, tentative, still assembling. Instead, Webb's NIRCam and NIRSpec stare at faint smudges and find compact, hyperdense cores already lit by supermassive black holes as heavy as, or heavier than, the one in the Milky Way. The expectation was gentle childhood. The observation is violent adolescence. In those early nuclei, spectra show furious star formation, wrapped around chaotic gas flows. Rings of newborn stars, jets of energy punching out, winds so intense they threaten to blow galaxies apart almost as fast as they grow. Our own galactic center, with its bar of stars and relatively calm surroundings, starts to look like the quiet suburb, not the template. Tonight we're going to use that contrast to see a pattern that runs through the entire history of astronomy. Build a new instrument, push to a new boundary, look in a new wavelength. Every time, the universe answers with, You've not been thinking big enough. Voyager did it at the fringe of the solar system. Webb is doing it at the fringe of cosmic time. By the end of tonight, you're going to understand that JWST's discovery of these alien galactic hearts is not an isolated shock. It is the latest chapter in a long tradition of reality-humbling theory, of space refusing to fit inside our neat diagrams. You're living in a uniquely compressed moment, where our mental map is expanding in both directions at once, outward as Voyager traces the true shape of the heliosphere, and backward as Webb sketches the first cities of stars at the universe's horizon. And if the edges we've already crossed were this surprising, what happens when we aim for the next boundary, one we haven't even named yet? That unnamed boundary is exactly where Webb has been looking, not at the edge of the solar system this time, but at the edge of the observable universe, where tiny pinpricks of light hide entire galaxies with hearts nothing like our own. Tonight, we're going to step back from the data and look at what you now carry in your head. By the end of tonight, you're going to understand that when scientists say galactic center, they are no longer just talking about the calm, bar-shaped hub of the Milky Way. They're talking about a whole family of hearts, and some of them are wild. In this mission, Webb did what no previous spacecraft or telescope could. It rewound cosmic time to less than 1 billion years after the Big Bang, and focused on one faint smudge near the universe's horizon. Expectation. A baby galaxy with a modest black hole and a loose growing core. Reality. A galactic center utterly unlike ours, with an overmassive black hole, an ultra-compact core, and violent activity that turns the whole system into a gravitational engine. You've seen 7 discoveries snap together into a single picture. The black hole is growing too fast, reaching Milky Way, scale masses when the universe is still in its infancy. The central region is packed to an extreme density, cramming stars, gas, and dark matter into a volume that would swallow our inner planets many times over. Around that heart, Webb's infrared eyes revealed starburst rings, where stars ignite in frantic waves and chaotic gas flows, spiraling, colliding, and feeding the central monster. The feedback is fierce. Outflows and radiation from the core carve channels through the surrounding medium, blowing a local wind into intergalactic space. Yet, wrapped around all this violence, the structures look strangely mature. Disks, bulges, and lanes that resemble grown-up galaxies, assembled long before standard models said they should exist. Even the way mass is distributed hints at dark matter playing a more intricate role than the simple scaffolding diagrams in textbooks. Put together, these discoveries challenge the usual story of co-evolution. The neat picture said black holes and galaxies grow hand in hand, slowly, in step. Webb's data say, no one expects this pace, no one predicts this level of concentration. Absolutely no one anticipates such a massive organised centre so early. Early galactic hearts lived fast and intensely, burning through gas, sculpting their surroundings, and setting the terms for everything that followed. And now, your sense of home has shifted. The Milky Way's relatively calm centre, with its modest star formation and gentle winds, may be the exception, not the rule. Galactic center no longer means one quiet radio source in one familiar system. It means a spectrum of hidden hearts, from serene to catastrophic, scattered across space and time. All of this from a point of light at the universe's edge. That is the humbling part. The idea that a signal crossing 13 billion years can reach a mirror near our small blue planet and rewrite the story of our own neighbourhood. If this is what one early heart can do to our models, what will happen when Webb finds dozens? Now, let's begin to ask what those future discoveries might reveal about the ultimate fate of galaxies like ours. If one distant heart can shake our picture of the Milky Way's core, what happens when there are hundreds? Thousands? When every deep field becomes a census of alien galactic centres, each one a different answer to the same question. How does a universe build a heart of gravity and fire? Tonight we're going to stretch that thought all the way forward. Because if scientists can already weigh black holes and trace starburst rings in galaxies whose light began its journey before our solar system existed, that means the real age of understanding is only just opening. Designed to glimpse a few rare, bright galaxies, Webb is now revealing entire populations. The expectation was a gentle rise in complexity. The reality is a sudden cliff. Before we get started on what comes next, pause on what has already been discovered. In less than a few years of operation, this one spacecraft has exposed overmassive black holes sitting in compact, turbulent cores less than 1 billion years after the Big Bang. It has mapped rings of furious star formation wrapped around those cores, where gas collapses into new suns at rates the Milky Way can barely imagine. No one predicts that level of organisation that early. No one expects to see galactic centres acting like finished engines when the universe is still wiring the rest of the system together. So where does that trajectory lead? The next step is even earlier, pushing closer to 300, 200, perhaps 150 million years after the Big Bang, until the first black hole seeds come into view. Some may be the collapsed remnants of the very first stars, others might be direct collapsed giants, born already massive from pristine clouds of hydrogen. By the end of tonight, you're going to understand that for astronomers, those are not just exotic categories. They are branching paths that determine how fast galaxies grow, how quickly heavy elements appear, how soon rocky planets can exist. But there is another path, the one absolutely no one anticipates. The possibility that Webb and the missions that follow it uncover central engines that do not fit either story. Black holes that are too light where they should be heavy. Nuclei that glow without any obvious accretion disk. Starburst rings ripped into spirals by winds that seem to come from nowhere. A new kind of object that needs a new name. So tonight, somewhere 13 billion light-years from here, that alien galactic heart is still burning. Its supermassive black hole is still anchoring a hypercompact nucleus of gas and stars in a galaxy that was barely old enough to have built itself. Photons are still streaming away from it in every direction, threading through the expanding universe, occasionally catching a mirror somewhere, occasionally not. The data has been on its way since before the Earth existed. The Milky Way's own quiet centre, with its 4 million solar mass Sagittarius A sipping slowly at the gas around it, is still doing the same thing it has been doing for billions of years. The contrast between the two does not change because we measured it. The universe simply produced both. There is something steadying in that. The catalogue of the galactic centres is bigger than anyone realised. The Milky Way's gentle bar and modest nucleus are one entry in that catalogue, not the template. Some hearts grew fast, some grew slowly, some grew in ways nobody has named yet. The next deep field will add more entries. The next telescope will resolve more detail. The next generation of cosmologists will inherit a richer atlas than we have, and they will look back at this moment as the year the map started to fill in. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.